In this podcast, we're going to talk about fission and fusion. All right, so energy and mass. What is nuclear energy? Well, whenever a change occurs in the nucleus, we see a small but measurable loss of mass. The mass that we lose is called the mass defect. And this mass is converted to energy according to Einstein's equation, E equal mc squared. M is for mass, the change in mass. E is the change in energy. And C is the speed of light. Because the speed of light, and then you square it, is so large, even small amounts of mass are going to be converted to enormous amounts of energy. So if we split an atom, you have a change in mass that results in a large change in energy. All right, so we have fission and fusion. Fission is when you split a heavy nucleus into two smaller nuclei that have smaller masses. And fusion is when you take two small nuclei and you combine them to form a heavier, more stable nucleus. So in the top one, we have uranium, which is radioactive. It is bombarded with a neutron, and it splits and makes barium and krypton, and then gives off 3 neutrons. Down here, fusion, you have a helium and a hydrogen, and they combine to form a helium-4. Okay, so a larger helium, different isotope of helium nucleus, and then they emit an electron. All right, so here's another schematic of fission. Here you have a uranium-235 atom. It's going to absorb a neutron, and it's going to split into a 238 uranium and a 235 uranium and release 2 neutrons and some energy. Okay, so we get some energy release there. Okay, then you're going to have another neutron that was emitted by that first reaction is going to be absorbed by the uranium 235 that was produced during the first, and then that's going to again create another fission reaction, and so it becomes a process that is self-maintaining, self-regulating, because you see it becomes a chain reaction. So this reaction up here, neutron meets with a uranium, splits, you have a release in energy, you release the uranium-238 that does not end up continuing in the reaction, and then you have uranium-235. He is going to absorb one of the neutrons that was let off, and then you have another release in energy, and it goes on so on and so forth. Okay, so every time you have a fission reaction, it basically ends up in a chain reaction that can continue. This is how nuclear power plants harness energy. All right, fusion is the opposite. We see fusion in stars. So in fusion, if you were to take 2 different isotopes of hydrogen, hydrogen-2 and hydrogen-3, and fuse them, you could make a helium-4, which is the stable isotope of helium, and you'd have 1 extra neutron left over. This is going to produce, fusion will produce energy up until a certain point, and then past a certain point, it requires energy. So up until iron fusion, so up until the production of iron, you can get energy from a fusion reaction, which is how stars have their energy. They have fusion reactions going on inside. And then once you reach iron, iron is the end of the producing energy fusion reactions. Everything else beyond that fuses, beyond iron, will require energy to be put in to actually make the reaction occur. All right, here is an example of a carbon-nitrogen-oxygen cycle inside of some stars that are heavier than the sun. And we see that continually hydrogen and helium atoms, or actually hydrogen atoms, are added to nuclei to produce even bigger nuclei. And then they release, like down here, we go nitrogen, oxygen, nitrogen, and then we have one come in, we release an alpha particle or a helium nucleus, and then we become carbon again, and it just keeps going over and over and over again. This is one of my favorite pictures because it shows a complete process of a massive star. Once a massive star is near the end of its life cycle, you get this onion structure. So here you have the hydrogen that was made, the helium, the carbon, the nitrogen, not nitrogen, neon, oxygen, silicon, and iron. Iron, I told you, was the end of the star life cycle because beyond that, it's going to require energy to get fusion. So up through all these rings, we were making energy. We were combining atoms and getting energy out. So here you see a couple of examples of some of the reactions that occur in the carbon, neon, oxygen, and silicon layers of the star. Okay, so fusion is very important in the solar system.